In this lesson, we will discuss quadratic congruences mod a prime number p, and we will define quadratic residues. So first, let's consider a quadratic congruence written in standard form. Ax squared plus bx plus c congruent to 0 mod p, where p is an odd prime, I'm further going to assume that a is not divisible by p, so a is not congruent to 0 mod p. I need this condition on a so that I can multiply by the inverse of a. So I'm going to rewrite this congruence by completing the square. So I'm first going to multiply by a inverse. So I have the x squared plus a inverse bx plus a inverse c is going to be congruent to 0 mod p. Then let me get the constant term on the other side. So x squared plus a inverse bx is going to be congruent to negative a inverse c mod p. And now I'm going to complete the square. So typically you would take the coefficient of x and divide it by 2 and square it. That'll work as long as a inverse b is even. So if a inverse b is not even, we can just add p to it because p is odd. And so we can always have a residue of the middle coefficient that's even. So I'm going to add the quantity a inverse b divided by 2 and then square it. I'm going to add that to both sides. Again, if a inverse b was not even, we could have just replaced it with a residue that is even. So we've completed the square, so the left-hand side will now factor as x plus a inverse b over 2 quantity squared, and this will be congruent to this expression on the right, which I'm going to replace with capital D, some number d, which really stands for the discriminant. If I make a change of variable, I reduce this to an equation that looks like y squared is congruent to some number d mod p. So the quadratic congruence that we began with can be simplified to one of the form with a variable squared congruent to a number mod p. And these are the types of quadratic congruences that we're going to study in this lesson. So let me show you how this works with a real quadratic congruence. So suppose we want to solve the congruence 3x squared plus 5x plus 6 congruent to 0 mod 11. Okay, as we saw above, I'm going to multiply by 3 inverse. Well, the inverse of 3 mod 11 is 4. So I multiply everything by 4, and I get 12x squared plus 20x plus 24. That's congruent to 0 mod 11. And I can reduce the 12. 12 is congruent to 1. And I'm going to leave 20 alone because I needed an even middle coefficient. And then I'm going to reduce 24 to 2 mod 11. Then getting the constant term to the other side, this is congruent to negative 2 mod 11. Now we complete the square. I'm going to take 20, divide it by 2, and square it, and I get 100. So by adding 100 to both sides, I obtain this congruence. So I've completed the square. The left-hand side now factors as x plus 10, the quantity squared, and this is congruent to 98, which is 1 less than a multiple 11. So I'm going to rewrite that as negative 1 mod 11. And again, making a change of variables, we see that the original congruence is solvable exactly when this last congruence is solvable. So if I can find a number, y, such that y squared is congruent to negative 1 mod 11, then I can solve for x. So what I'm going to do is I'm going to look at the square of all the numbers between 1 and 10 and reduce them mod 11. So now I'm going to square the numbers 1, 2, 3, all the way up to 10. And reduce them mod 11. Okay. Well, 1 squared is congruent to 1. 2 squared is congruent to 4 mod 11. 3 squared is congruent to 9. 4 squared is congruent to 5. And 5 squared is congruent to 3. Now, I only have to go up halfway because if I square 6, that's the same as squaring negative 5 mod 11. And we see that whether I plug in a plus or minus and square it, I'm still going to get the same 5 answers that I just obtained. So if I change these all to plus or minus 1 and plus or minus 2, or plus or minus 3, plus or minus 4, and plus or minus 5, then I've squared all the residues 1 through 10 mod 11. And we see that none of these answers are congruent to negative 1, which is 10 mod 11. So we see that the final congruence, y squared congruent to negative 1 mod 11, is not solvable, and therefore our original congruence is not solvable. So we'll soon figure out a way to determine if a congruence like this final congruence, y squared congruent to -1 mod 11, is solvable without going through and listing all the residues mod p. So from these previous examples, we see that any quadratic congruence mod an odd prime p can be reduced to one of the form x squared congruent to some integer a mod p. So now we'll be concerned with determining when this congruence is solvable. So this is the question that we're going to address. We'll notice something, that since the modulus p is prime, Lagrange's theorem tells us that this congruence can have at most two solutions. So the degree 2 tells us that there's at most two distinct solutions. But notice that if x is a solution to this congruence, then negative x will also be a solution. So we see that there's either 0 solutions or 2 solutions to every congruence of this form. So if x is a solution, so is negative x. Thus, there are either 0 solutions or 2 solutions. So we're going to be concerned with this type of congruence and when it's solvable to a great deal. And so we're going to make a definition. So given an odd prime p, and we're going to assume that a is not congruent to 0 mod p, if x squared congruent to a mod p is solvable, we'll call a quadratic residue mod p. We say that a is a quadratic residue mod p if this congruence, x squared congruent to a mod p, is solvable. So if we can find a value x such that x squared is congruent to a mod p, then we call a quadratic residue mod p. If we can't solve this congruence, if there is no x such that x squared is congruent to a mod p, then we call a quadratic non-residue mod p. Otherwise, we say A is a quadratic non-residue mod P. So there's quite some history involving quadratic residues. It goes back to the 17 and 1800s. Gauss did a lot of work in quadratic residues and non-residues, and we've already defined the word residue previously. So the names quadratic residue and quadratic non-residue are kind of misleading. It might be better to say that A is a square mod P, or A has a square root mod P. But as Levesque mentions in his book, that this language of quadratic residues is too firmly rooted in tradition. And so we'll stick to the names quadratic residue and quadratic non-residue. So let's look at a quick example of quadratic residues. Recall that when we work mod 11, plus or minus 1 squared are congruent to 1, plus or minus 2 squared are congruent to 4, plus and minus 3 squared are congruent to 9, plus and minus 4 squared are congruent to 5, and plus or minus 5 squared are congruent to 3 mod 11. So with this definition of quadratic residues, we see that 1, 4, 9, 5, and 3 are all quadratic residues mod 11. So these are the only possible quadratic residues mod 11. So all the other integers that are relatively prime to 11 must be quadratic non-residues. So that would leave 2, 6, 7, 8, and 10 as quadratic non-residues. So if you notice, there's the same amount of quadratic residues and non-residues mod 11. So this is an example of the next theorem. So if P is an odd prime, then there are exactly P minus 1 over 2 quadratic residues mod P and P minus 1 over 2 quadratic non-residues mod P. In the set 1, 2, 3 up to P minus 1. So it's actually a fact that in any reduced residue system mod P, exactly half of the residues are quadratic residues and half are quadratic non-residues. So let's prove this theorem. So let's consider the square of the first half of these numbers in this reduced residue system. So consider the numbers one squared, 2 squared, 3 squared, up to p minus 1 over 2, the quantity squared. So each of these numbers is distinct mod p. And we're going to show that the least positive residue mod p of these numbers represent all the quadratic residues mod p. So each of these numbers, first of all, is distinct mod p. In other words, none of these squares are congruent mod p. Why is this true? Well, because if you set two of these squares equal to each other, so for example, if x squared is congruent to y squared mod p, where x and y are both in this set, so 1 is less than or equal to x and y, and they're both less than or equal to p minus 1 over 2. If x and y are between 1 and p minus 1 over 2, and if x squared is congruent to y squared mod p, then I can subtract y squared from both sides. So I have x squared minus y squared is congruent to 0 mod p. And when I factor this difference of squares, we see that, and hence x plus y times x minus y is congruent to 0 mod p. Well, we proved that if a product is congruent to 0 mod prime, then one of the two factors must be congruent to 0 mod p. So then x plus y is congruent to 0 mod p, or x minus y is congruent to 0 mod p. But if you think about it, x and y are both between 1 and p minus 1 over 2. So x plus y must be greater than 1 and strictly less than p. So you can't have x plus y congruent to 0 mod p because it actually equals an integer between 1 and p. So therefore, x plus y cannot equal 0, cannot be congruent to 0 mod p. So we can conclude that x minus y must be congruent to 0 mod p. Thus x minus y is congruent to 0, and x is therefore congruent to y mod p. So this proves that each of these numbers that we started with is distinct mod p. So now let's consider the least positive residues of these numbers that we started with. Well, since the least positive residues of 1 squared, 2 squared, up to p minus 1 over 2 squared. The least positive residues of these numbers are all distinct quadratic residues mod p. We see that there must be at least p minus 1 over 2 quadratic residues mod p. So there's at least p minus 1 over 2 quadratic residues. And now I'll show that every quadratic residue must be congruent to one of these integers, 1 squared, 2 squared, up to p minus 1 over 2 squared. Therefore, they're going to be at most p minus 1 over 2 quadratic residues, and that will show that there has to be exactly p minus 1 over 2 quadratic residues. So let's continue. Now, notice that p minus k, the quantity squared, is congruent to k squared mod p for any integer k. So if you look at p minus k, the quantity squared, if you expand that, you get p squared minus 2pk plus k squared. And so the two terms that have a p, a factor of p, will be congruent to 0 mod p. So this shows that p minus k, the quantity squared, is just congruent to k squared mod p. So in other words, every quadratic residue must be congruent to exactly one of the numbers we started with, 1 squared, 2 squared, up to p minus 1 over 2 squared. Then every quadratic residue is congruent mod p to exactly one of the numbers 1 squared, 2 squared, up to p minus 1 over 2 squared. We show that these are all distinct mod p, and every quadratic residue must be congruent to one of them, so it has to be congruent to exactly one of these numbers. Therefore, there can be at most p minus 1 over 2 quadratic residues. We show that there's at least p minus 1 over 2 and at most p minus 1 over 2 quadratic residues. So therefore there must be exactly p minus 1 over 2 quadratic residues mod p. And this finishes the proof because from the original reduced residue system, the rest of those integers must be quadratic non-residues. So exactly half are quadratic residues and half are quadratic non-residues. So this completes the proof of the theorem. So let's illustrate this again with another prime. When p is 13, let's look at the integers 1 through 12, Well, as we know, we only have to square the first half of them. So let's look at 1 squared is congruent to 1 mod 13. Okay. 2 squared is congruent to 4. 3 squared is congruent to 9. 4 squared is congruent to 16, which is 3. 5 squared is congruent to 12 mod 13, and 6 squared is congruent to 10 mod 13. So therefore, the numbers 1, 4, 9, 3, 12, and 10, those are all quadratic residues mod 13. And let's put them in order. So 1, 3, 4, 9, 10, and 12 are quadratic residues. Mod 13, and the other integers between 1 and 12 would therefore be quadratic non-residues. So 2, 5, 6, 7, 8, and 11 quadratic non-residues mod 13. And this is another example of this previous theorem. Exactly half of the reduced residue system mod 13 are quadratic residues and half are quadratic non-residues. So next we will present Euler's criterion for determining when an integer is a quadratic residue mod p. But before we do that, I want to point out something. Here's a little note. If a is not congruent to 0 mod p, and again we're going to assume p is an odd prime, I'm going to let y equal a to the p minus 1 over 2 power. Then notice something. If I square y, so y squared, that will equal a to the p minus 1 over 2 quantity squared. And this just simplifies to a to the power p minus 1. Well, what does Fermat's little theorem tell us about this quantity? We know that this quantity must be congruent to 1 mod p. So look at this. So y squared is congruent to 1 mod p. Well, we showed in a homework exercise that the only solutions for y are plus and minus 1 mod p. So y is congruent to plus or minus 1 mod p. And we'll see from Euler's criterion that if a is a quadratic residue mod p, then y will be congruent to 1 mod p, and if a is a quadratic non-residue, then y will have to be congruent to negative 1 mod p. So let's present Euler's criterion. Given an odd prime p, and an integer a that is not congruent to 0 mod p, then Euler's criterion states that x squared congruent to a mod p is solvable, which is equivalent to saying that a is a quadratic residue mod p, okay, so x squared is congruent to a mod p is solvable if and only if a to the power p minus 1 over 2 is congruent to 1 mod p. So as I just pointed out, if a to the p minus 1 over 2 is not congruent to 1 mod p, then it must be congruent to negative 1 mod p. So we can also say that x squared congruent to a mod p is not solvable if and only if a to the p minus 1 over 2 is congruent to negative 1 mod p. Okay, so this is Euler's criterion. So we can quickly calculate a to the p minus 1 over 2, and if it's congruent to 1 mod p, then a is a quadratic residue mod p. So we begin the proof with the forward implication. Let's assume that x squared congruent to a mod p is solvable. So if x squared is congruent to a mod p, then a to the power p minus 1 over 2 is congruent to x squared to the power p minus 1 over 2. And the 2's cancel, and that just equals x to the power p minus 1. And again, by Fermat's little theorem, this is congruent to 1 mod p. So we see that if a is a quadratic residue mod p, then a to the p minus 1 over 2 will be congruent to 1 mod p. Now let's prove the converse. So I'm going to assume that a to the power p minus 1 over 2 is congruent to 1 mod p. So suppose a to the power p minus 1 over 2 is congruent to 1 mod p. Since p is prime, we know that p has a primitive root mod p, and we know that the powers of a primitive root will generate a reduced residue system mod p. So therefore I can write a as a power of a primitive root. So first let g be a primitive root mod p. We know that g exists, and then we know that g to the powers of g generate all the integers that are relatively prime to p. So then we can write a. Then a is congruent to g to the k mod p for some integer k. Now I claim that this exponent k must be even. K is even. Okay, let's give a proof of the claim. Since g to the power k times p minus 1 over 2 is equal to g to the power k, the quantity to the power p minus 1 over 2, which is congruent to a to the power p minus 1 over 2. And we're assuming this is congruent to 1 mod p. Then we see that g to the power k times p minus 1 over 2 is congruent to 1 mod p. Well, we showed that if that's true, then k times p minus 1 over 2, and this exponent k times p minus 1 over 2, must be congruent to 0 mod p minus 1. So in other words, p minus 1 divides k times p minus 1 over 2. So we can write k times p minus 1 over 2 as some integer times p minus 1. It's called n times p minus 1. Some integer n. Then if I divide both sides of this equation by p minus 1, we see that k over 2 is equal to the integer n, and I can write k as 2 times the integer n. But by definition, k is even. Okay, so I've shown that if a is congruent to g to the k mod p, where g is a primitive root, then k must be even. So I'm going to replace k with 2n. So that finishes the proof of the claim. Now let's go back and finish our other proof. Therefore, a, which is congruent to g to the power k, and now I'm going to replace k with 2 times some integer n, and that is congruent to g to the power n, the quantity squared, mod p. But we see that g to the power n, the quantity squared, is congruent to a mod p. That makes g to the power n a solution to the congruence x squared congruent to a mod p. So g to the n is a solution to the congruence x squared congruent to a mod p. And therefore, a is a quadratic residue mod p. And this finishes the proof of Euler's criterion. So Euler's criterion is very useful. It gives us a calculation to verify if an integer is a quadratic residue mod a prime. Let's look at a quick example of Euler's criterion. So let's see if 11 is a quadratic residue mod 17. So is 11 a quadratic residue mod 17? Well, by Euler's criterion, we just have to simplify 11 to the power 17 minus 1 over 2 mod 17. Well, this is 11 to the power 8, and if you multiply this out, this is actually going to be congruent to 16 mod 17, and 16 is negative 1 mod 17. So therefore, 11 is a quadratic non-residue mod 17. So by Euler criterion, you'll either get 1 or minus 1 mod the prime p. When a to the p minus 1 over 2 is congruent to 1 mod p, then it's a is a quadratic residue, and otherwise a is a quadratic non-residue. This next theorem provides a formula for a solution to x squared congruent to a mod p in the case when p is congruent to 3 mod 4. So if p is congruent to 3 mod 4, if p is prime, and we know that x squared congruent to a mod p is solvable, then a solution is given by x congruent to a to the power p plus 1 divided by 4. Then x congruent to a to the p plus 1 over 4 is a solution. And recall that if x squared congruent to a is solvable, there has to be exactly 2 solutions. So here's one solution. The negative of this x would be another solution. So as a quick note, negative x is the other solution. Okay. So let's prove this. First, let's consider the case when a is congruent to 0 mod p. So if a is congruent to 0 mod p, then this expression x, which is congruent to a to the power p plus 1 over 4, will still just be congruent to 0, and 0 squared is congruent to 0, so this is still a solution. Okay, so if a is congruent to 0 mod p, then 0 is the solution. So now let's suppose that a is not congruent to 0 mod p. Well, since x squared congruent to a mod p is solvable by Euler's criterion, we know that a to the power p minus 1 over 2 must be congruent to 1 mod p. So since x squared is congruent to a, mod p is solvable, Euler's criterion tells us that a to the power p minus 1 over 2 must be congruent to 1 mod p. Okay, so now let x be congruent to a to the p plus 1 over 4. Then x squared which equals a to the p plus 1 over 4, the quantity squared. If I simplify the exponent, this will just be equal to a to the p plus 1 over 2. And I can break up this exponent. This is the same as a to the p minus 1 plus 2 over 2 exponent. If I break this up, I get a to the p minus 1 over 2 plus 1 exponent. So this is a to the p minus 1 over 2 times a to the first power. But this a to the p minus 1 over 2 is congruent to 1 mod p. So we just get, this is congruent to a mod p. And we've just verified that a to the p plus 1 over 4 is a solution to the congruence x squared congruent to a mod p. So let's see an example of this theorem. So recall I mentioned that instead of saying that a is a quadratic residue mod p, it might be better to say that a has a square root mod p, or that a is a square mod p. So we can ask questions like this: find the square roots of 5 mod 11. So if you think about how we define square roots, so a number is a square root mod 11 if when you square it, you get 5 mod 11. So in other words, I could have just said solve the congruence x squared congruent to 5 mod 11. I'm going to use the previous theorem to find a solution. 11 is congruent to 3 mod 4, and 5 is a quadratic residue mod 11, so we can solve this. So since 11 is congruent to 3 mod 4, by the previous theorem, one solution is x congruent to 5 to the power 11 plus 1 divided by 4. So that would be 5 to the power 3, which is 125. And when we reduce mod 11, see this is 4 more than a multiple 11, so this is 4 mod 11. So one square root of 5 mod 11 is the integer 4. And we see that if I square negative 4, I also will get 5 mod 11. So the square roots of 5 mod 11 are plus or minus 4. Now this next example will answer the same type of question about square roots, but the modulus will be composite. So now let's find the square roots of 71 mod 77. So what we need to do is to solve the congruence x squared congruent to 71 mod 77. So what we're going to do is solve the congruence with a smaller modulus, because 77 is 7 times 11. We're going to first solve the congruence mod 7 and mod 11, and then we're going to combine the solutions. So we'll combine the solutions and we'll get solutions to the congruence mod 77. So let's first solve the congruence x squared congruent to 71 mod 7. Well, if I'm working mod 7, then 71 is congruent to 1 mod 7. And we know that the only solutions to x squared congruent to 1 mod 7 would be plus or minus 1. So x is congruent to plus or minus 1 mod 7. Now let's solve this congruence mod 11. So if x squared is congruent to 71 mod 11, then 71 is 5 more than a multiple 11. So this is the same as x squared congruent to 5 mod 11. And the previous example, I showed that the solutions to x squared congruent to 5 mod 11 are plus or minus 4. So x is congruent to plus or minus 4 mod 11. So each of these congruences mod 7 and mod 11 have two distinct solutions. And we'll see when we combine these four solutions, mod 77, we're actually going to get four distinct solutions mod 77. So now I'm going to combine the solution x, which is congruent to 1 mod 7, and the solution x congruent to 4 mod 11. So I want to find a residue mod 77 that's 1 mod 7 and 4 mod 11. So I'm just going to keep adding the modulus until I get a common number. So if I add 7 to 1, I get 8. If I add 7 again, I get 15. And now I notice that if I add 11 to 4, then that's also congruent to 15. So we see that x congruent to 15 mod 77 is a solution to the original congruence. So 15 is a square root mod 71. And if I know that 15 is a square root of 71, then negative 15 must also be a square root of 71 mod 77. So if I produce one solution, then I can automatically just take this negative and get another solution. Now let's try combining x congruent to 1 mod 7 and x congruent to negative 4 mod 11. Again, I'm just going to keep adding the modulus, so I get 8, which is congruent to 15, which is congruent to 22, which is congruent to 29, and this is also congruent to negative 4 mod 11, because if I add 11, I get 7. 7 plus 11 is 18. 11 plus 18 is 29. So we see that if x is congruent to 29 mod 77, then it'll be also congruent to 1 mod 7 and negative 4 mod 11. So x congruent to 29 mod 77 is a square root of 71 mod 77. And likewise, x congruent to negative 29 is also a solution. And you can verify that if you combine x congruent to negative 1 mod 7 and plus or minus 4 mod 11, you'll get the same set of answers. You'll get either plus or minus 15 and plus or minus 29. So therefore, the 4 square roots of 71 mod 77 are plus or minus 15 and plus or minus 29.